SpaceX is redefining the space industry, making rockets reusable and pushing the boundaries of what's possible. In a previous video dedicated to SpaceX catching the Starship's booster with robotics arms, I broke down some of the control engineering problems that SpaceX engineers needed to solve to achieve that feat. All these problems boil down to very complex mathematical problems. But obviously, mathematical problems are useful only if they can be solved, and solved very, very fast. If you're influenced by Hollywood, maybe you're thinking of some genius person like Einstein with pen and paper scribbling down equations. But no, the reality is that you cannot solve these kind of problems with pen and paper. And there is no human who can solve them. Practically, these problems are solved using computers and a special mathematical tool called optimization. Hi everyone, this is Dr. Giordano Scarciotti. I'm an academic at Imperial College London and I happen to be the director of the MSc in Control and Optimization. I teach a course called Advanced Applied Optimization. In this video, we will explore how SpaceX uses optimization, and in particular convex optimization, to solve complex engineering problems like landing rockets, optimizing fuel use, and planning safe trajectories through space. I will try to give the core ideas behind convex optimization so that you can see how it works and how it's helping SpaceX achieve the impossible. Let's start with the basics. What is optimization? In simple terms, optimization is the process of finding the best solution to a given problem from a set of possible choices. Imagine you are controlling a rocket and you want to use the least amount of fuel to reach orbit. The problem of finding the exact path or trajectory that minimizes fuel consumption is an optimization problem. You have a goal, minimizing fuel, and constraints like the physics of the rocket dynamics and fuel capacity. And your task is to find the best possible solution within those constraints. Optimization problems are everywhere, from deciding how to distribute resources efficiently to determining the most cost-effective way to manufacture a product. They all involve maximizing or minimizing a certain quantity, whether it's cost, energy, time, or something else. Now that the concept of optimization is clear, let's move on to a more specific type of optimization problem that is particularly important for solving complex engineering challenges: convex optimization. So what is convex optimization? Convex optimization is a branch of optimization where we deal with mathematical functions that have a special property. Their shape is convex. In simple terms, you can visualize convexity by thinking about a giant ball. If you stand at the center of this giant ball, you can see that the ball curves upward on all sides. On the other hand, wherever you are on the sides, you know that the lowest point is right beneath you. In mathematical terms, a convex function is like this ball. It has a unique minimum point that is globally optimal. This means that there cannot be a point smaller than that point. This is different from this other figure where there is a global and a local minimum. A point that looks the best if you stand close to that point, but it is not really the best. If you find the global minimum, you can be sure it's the best solution to your problem. In convex optimization, we aim to minimize or sometimes maximize a function while satisfying certain constraints. These constraints could be physical limitations like the maximum thrust a rocket can provide, or they could be related to the problem's geometry, like ensuring that the rocket doesn't hit any obstacles on its way to space. What's really powerful about convex optimization is that it guarantees that the solution we find is the best possible one. Unlike non-convex problems where there might be many local minima, convex problems only have one global minimum. This makes solving them much more efficient because if you see down, you know for sure that that's the direction to go. And that's why aerospace engineers use these methods to make real-time decisions during their missions. Now let's be more concrete and explain where and how this is used when flying rockets. In my previous video, we talked about how control engineering achieves trajectory tracking, which is the problem of steering the rocket on a planned trajectory. But how do engineers know what the right trajectory is? One of the most crucial uses of convex optimization in space flight is in trajectory optimization. Imagine a Falcon 9 rocket taking off. Its path, or trajectory, is like a giant arc curving into space. But what most people don't realize is that there are many possible trajectories that the rocket could take. Some paths use more fuel, others may not reach the target orbit, and some could even lead to mission failure. The goal of trajectory optimization is to find the most efficient path, one that minimizes fuel consumption while ensuring that the rocket reaches the desired orbit. This problem can be formulated as a convex optimization problem. The objective is to minimize fuel use, and the constraints include things like the rocket's physical limitations, aerodynamic forces, and the need to avoid obstacles or collisions. Let's try to understand the maths behind this. Think of the rocket's trajectory as a sequence of states, its position, velocity, and fuel levels over time. We indicate the collection of states with the letter X. The trajectory is influenced by the control inputs indicated by the letter U. The inputs is how much thrust to apply and in what direction at each moment. The optimization problem can be described mathematically by a cost function that represents fuel use that we want to minimize, and a set of constraints defined by the rocket's dynamics. This leads to what's known as a constrained optimal control problem. This is formulated on this slide. The objective function that we want to minimize is the total fuel consumption. The fuel consumption is typically proportional to the integral of thrust, indicated with the letter U, over time, specifically from time 0 to time capital T. You may not be familiar with what an integral is, but in simple terms you can imagine that the integral is a way of taking into account the entire history of U, so that we minimize the entire use of thrust and not just the thrust at this moment in time. Then you can see that U is surrounded by two bars. That is a mathematical operation called norm that you can think of as taking the square of U, so multiplying U by itself. Why do we take the square? Because mathematically it is easier to deal with squares and it doesn't change very much the result. Now that we understood the objective function, let's move to the constraints. The first constraint is the dynamics of the rocket, which essentially means that we need to incorporate in our problem a mathematical model of the rocket. This is represented by a differential equation. Again, you might not be familiar with differential equation, but you can simply think that the equation tells us that x must evolve according to a law described by f. F is a function which is a mathematical relation involving the current x and u. There is some additional information that we need to specify in the problem, and these are additional constraints. We need to tell the problem the initial state of the rocket, indicated by x0, and we need to indicate the final state, x of capital T. For instance, the initial state will be the position of the rocket at the launch pad, while the final state will tell us what the final altitude and position must be. We also have a constraint on the amount of thrust that can be exerted at every instant of time, and this is a limit due to either the physics of the rocket or the amount of fuel that can be burned at a given moment. This constraint is represented by saying that the norm of U must be less than a given maximum value. Finally, we may want to avoid obstacles or certain regions of space. The way this is done is by constructing a mathematical function which is positive when the rocket is in that forbidden region or when it's close to an obstacle. We call this function h, and we impose that the function is less than or equal to 0, meaning that we must be clear of these obstacles. So this is the final optimal control problem, and in particular, it is an example of continuous time optimal control problem. Continuous time refers to the variable t appearing all over the place and representing our actual real time, that is, a continuous flow of time. The issue, however, is that continuous time optimal control problems are difficult to solve. In general, we do not know how to find a U that minimizes the objective function and satisfies all the constraints. This is an active area of research in control engineering and mathematics. And this is where convex optimization plays a crucial role, because it allows us to find an approximate solution. To solve the problem, we use a three-step procedure. The first step in applying convex optimization to these continuous time problems is discretization. In discretization, we break down the continuous problem into a series of discrete steps, converting the time domain from continuous to discrete time steps. This converts the system dynamics and control inputs from continuous functions into sequences of states and controls over discrete time intervals. For example, the integral of u, which is the area under this curve representing u, is discretized by an approximation in which we break down the time in discrete intervals of size delta t, and then we compute the area of the rectangles above these intervals. Essentially, it is like to change u with an approximated version, where we pick the value of u at time k delta t, and we freeze it for delta t seconds. Then we make an update and repeat. So in the end, the integral goes from being something that we don't know how to compute to just the sum, indicated by this mathematical symbol, of all the areas of these rectangles. The other equation that we need to discretize is the dynamics. If you remember, the equation of the dynamics tells us that x evolves according to a law represented by f. A discretization of this equation is the following, where with x of k plus 1 we mean the value of x at the next time, and with x of k we mean the value of x at the current time. Then the equation is telling us that we can compute x at the next time from x at the current time, and that this update is computing using the product of f and delta t. Discretization is an approximation, of course, as it is clear from the plot of the integral. But this is an approximation that can be made as precise as we want by decreasing the discretization time delta t. The resulting discrete time problem is much simpler. The reason is that in the continuous time problem we need to find u for all times. Since time is a continuous flow, we need to look for a large number of options. In fact, we need to look for an infinite number of options. But once we discretize, we just need to look for u at times k delta t. So we just need to find a number of values of u equal to capital T divided delta t. In summary, a small delta t gives a better approximation, but it results in a problem with more variables, because the number of variables is capital T divided delta t. This concludes the first step. And the second step is convexification. Many practical rocket control and trajectory problems are naturally non-convex. To apply convex optimization, these problems are often convexified, which means we approximate the original non-convex problem with a convex one. This approximation still captures the essential characteristics of the original problem, but allow us to use efficient convex optimization techniques. I will skip here the mathematics and I will just represent this idea with a figure. We can start with a non-convex function, the one in red, and we can look for a close approximation that is instead convex. For instance, the one in blue. If we do this for all the maths appearing in the problem, then the problem becomes a convex optimization problem. At this point, we apply the third step. The convex problem is solved. Now, I need to give you a disclaimer. Even though convex optimization is extremely useful and I'm covering the main ideas in this video, a full understanding of what convex optimization is, how it works and how to use it is complicated and requires the level of competence of a senior engineering student. So I will not go into more mathematical detail in this video. However, if you are interested, let me know in the comments below and subscribe to the channel, and I will release a series of lectures on the topic. Now let's go back to space. In spacecraft landing problems like SpaceX Falcon 9 landing, convex optimization is applied through successive convexification. Here is how it works. The original nonlinear non-convex problem is convexified around a feasible nominal trajectory. Then a convex optimization problem is solved for that nominal trajectory, and then the solution is used to update the nominal trajectory, and the process is repeated, iterating between convexification and solving convex problems until convergence. This method ensures that even though the original problem is non-convex, it can be solved by solving a series of convex problems. This technique is an example of sequential convex programming. As just explained, and in other words, sequential convex programming works by breaking down the problem into smaller convex subproblems, solving each one in an iterative way to get closer to the optimal solution. This approach is computationally efficient and well suited for real-time applications, which is critical for something as time-sensitive as rocket control. As explained in my previous video, the landing problem can be formulated as a model predictive control problem, called for short MPC. In MPC, we need to compute the optimal control inputs, like thrust, direction, and magnitude, to guide the rocket safely to its landing spot. If you remember, the idea of MPC was first to find the best control input over a finite discretized horizon, second, apply the found input at the first time step, and third, repeat this procedure over a new time horizon shifted by 1 in the future. But how does MPC find the optimal control input in a given horizon? MPC may use convex optimization to solve this problem in real time, updating its calculations every few milliseconds. The rocket's onboard computer predicts how the rocket will move over the next short time horizon, based on its current velocity, altitude, and external factors like wind. The computer then solves a convex optimization problem to determine the best control inputs that minimize the distance to the landing pad while keeping the rocket stable. Since gusts of wind or minor variation in engine performance can push the rocket off course, MPC combined with convex optimization continuously recalculates the optimal trajectory based on new sensor data, ensuring that the rocket makes small, precise adjustments in real time. This combination of prediction, optimization, and control is what allows these rockets to land with pinpoint accuracy. And if you are curious about what objective function can be used for this task, here is a formulation of the problem. This formulation has already been discretized. It is interesting to see that this objective function is the sum of two terms. The first term is the difference between x, which is the state of the rocket, and xd, which is the desired trajectory. The desired trajectory is the planned trajectory that we have found before from the trajectory optimization problem. But as you can see, in this objective function, we also sum the thrust magnitude. What does this mean? Well, to move the rocket and so push x to the desired trajectory, we need to use thrust. The more thrust we use, the faster we obtain the desired trajectory. If we had only the first of the two elements in the objective function, then the rocket will use a huge amount of thrust to minimize the distance from the desired trajectory as fast as possible. This will most likely result in using too much fuel. Thus, by adding the second term, we are adding a competing objective. We are telling the problem, I want that you get close to the desired trajectory, but please don't use too much thrust, and consequently fuel. At this point, we have covered quite a few problems in good detail. Let's quickly go through a couple more problems without giving the mathematical details. The first problem is attitude control. Rockets and spacecraft rely on control systems to maintain their orientation, and this problem is known as attitude control. For SpaceX, attitude control is essential not only for pointing the rocket's engines in the right direction, but also for precise maneuvering during docking, orbital directions, and landing. Convex optimization helps solve attitude control problems efficiently. The control system needs to adjust the rocket's thrusters or fins to keep it oriented correctly. But the rocket can rotate in multiple directions, so we have to solve an optimization problem to determine the best sequence of control inputs that minimizes fuel use while achieving the desired orientation. This problem can be formulated using convex optimization in a similar fashion explained for the other problems. The second problem is launch window optimization. SpaceX doesn't just launch rockets whenever they feel like it. Instead, each mission has to carefully select the optimal launch window. This is the period during which launching the rocket ensures it can reach its target orbit efficiently, using the least amount of fuel. This is another optimization problem, this time in the domain of orbital mechanics. The launch window depends on many factors: the rotation of the Earth, the orbit of the target satellites, and in the case of interplanetary missions, also the position of celestial bodies like the Moon and planets. Convex optimization is used here to solve a time-optimal control problem. That means finding the best time to launch that minimizes the amount of fuel needed to reach orbit, while ensuring the rocket arrives at its destination on time. And of course, this is a complex problem that requires solving equations that model the rocket's motion through space, the gravitational influence of other bodies, and the constraints on the rocket's propulsion system. But yet again, optimization helps to find a solution to this challenging problem. Convex optimization isn't just for today's rockets, it's also a big part of SpaceX's future plans. As the company looks toward interplanetary travel, convex optimization will play an even bigger role. For missions to the Moon, Mars, and beyond, SpaceX will need to optimize fuel use over long distances, plan complex trajectories through the solar system, and perform precision landings on alien worlds. Convex optimization provides the tools to solve this kind of large-scale, multi-stage problems efficiently. But I want to stress that convex optimization has a much wider impact that goes way beyond rockets. This is not just about SpaceX, it's about the power of mathematics to solve real-world problems. Convex optimization is used in industries like finance, robotics, machine learning, traffic management, and so on. The principles behind it are universal. If you have a problem that involves minimizing cost, maximizing efficiency, or finding the best solution under constraints, convex optimization is one of the most reliable and useful tools at your disposal. In the modern world, convex optimization is shaping industries by providing efficient solutions to complex problems. The reason it's so powerful is that it gives us a way to make optimal decisions quickly, even when the stakes are high. Whether you are managing an investment portfolio, controlling a self-driving car, or of course, landing a rocket. Lots of people don't like mathematics, but the truth is that mathematics powers our world, and it will power our future more and more. Whether it's building cars, managing the traffic, controlling robots, or traveling to Mars, mathematics and specifically optimization will play a critical role. Thank you for watching and see you next time.